Okay, so we are going to start the solutions unit. So first thing we're going to talk about is electrolytes and non-electrolytes. You would have talked a little bit about this last year in Science 10 when you looked at electrical conductivity. So remember, we use little conductivity meters. They have like little two prongs, and you stick it on something or in a solution, and then you see if the light lights up. So what we find when we are talking about solutions, we either talk about solutions as being an electrolyte or as being a non-electrolyte. If we consider something to be an electrolyte, that means when we test its conductivity, it is going to conduct electricity. If we decide that it's a non-electrolyte, that means when we use the conductivity meter, the light does not light up and we do not conduct electricity. So when we are looking closely at the solution, what we find is that in an electrolytic solution, we are going to have ions present in solution. And that is why it's going to be able to conduct electricity, because we have these ions that have positive and negative charges and they're moving all over the place, so they are able to conduct electricity. Okay, when we look, I'm just going to change the color so you can actually see this. When we look at a non-electrolyte, this generally means that there are no ions. I didn't need to write up there, right down here, no ions. Okay, and that is why it is incapable of conducting electricity. Change that color. There we go. Okay. Oh, and now of course my slide's not going to line up in here. Hold on 2 seconds. We're going to shift the screen. There we go. So when we talk about solutions, we're going to talk about a couple of different types of solutions. We are going to talk about ionics, we are going to talk about moleculars, we are going to talk about acids, and we are going to talk about bases. Okay, you should be familiar with last year that pretty much all of those in solution conducted electricity with the exception of a molecular compound. And if you think about what we just talked about, we talked about how in an electrolytic solution, you are going to have ions. And in a non-electrolytic solution, you're not going to have ions. So why are we going to have ions when we have an ionic solution? So remember we watched that video when we talked about solutes and solvents and when we dissolve things, right? And we saw that that salt crystal went in and then all the individual ions got pulled off. So what happens when we put an ionic into water is it's going to dissociate. We say it dissociates because all the individual ions that were bound together in our solid are going to come off into separate ions. So we can write a dissociation equation. So in general, when we write a dissociation equation, we are going to have our compound. So let's say we take NaCl, and it's a solid, and we put this into water. So we're going to use our arrow, and over top of the arrow, we are going to write water. We're going to put it over the arrow because the water doesn't actually change in the reaction. It's just there to help dissolve it. So if you check your solubility table, which is something you should be doing when we are looking at solutions, you will see that sodium chloride is soluble. So that means it is going to dissolve. And as it dissolves, it's going to dissociate. So when this dissociates, it's going to break apart into the two ions. So because it's sodium chloride, the two ions are sodium ions and chloride ions. So a sodium ion is going to be an Na with a plus charge, because when we look at our periodic table, sodium has a +1 charge. Because it's now in water, we're going to give it an Aq subscript. And then our other ion is going to be the chloride. So it's a Cl with a negative charge. And it's also going to be aqueous. So we're going to have that the NaCl solid goes into water and turns into a sodium ion and a chloride ion. Okay, we can look at an example that has some subscripts because those look a little bit different. So let's say we had magnesium, let's go bromide. So it's going to be MgBr2. It's a solid. Okay, same deal, we're going to put it into water, so we're going to put our arrow. Over top of the arrow, we are going to write out the water. Okay, so remember as you watch these videos that if at any point in time you need to pause it because you want to write some stuff down, you can hit the pause button. You don't have to panic that it's moving along too quickly. So now what we're going to do is we are going to dissociate the magnesium bromide. So this is going to break apart and it's going to give me a magnesium ion, which is an Mg2+. Okay, again, it's going to be aqueous. So see how the bromine over here had a 2 subscript. Remember that that 2 subscript is only there to balance out those charges. It doesn't actually mean that the bromines are bound together. So when we write out our product side, the 2 is going to move to the front for balancing purposes. So in general, you're going to find that when you write dissociation equations, you are not going to have subscripts over here on the product side, because over here, the subscripts with this is just to tell me how many I actually needed. So when we dissociate it, how many is going to move to the front as the balancing coefficient. The only time I should really ever have any subscripts is going to be if I have a polyatomic ion. Then that subscript is part of the polyatomic ion, so it does get to stay. So let's say, for example, we had ammonium chloride. So NH4, Cl. Okay, same deal, solid. We're going to put it into water. So we have our arrow. Over top of that, we're going to write our water. Okay, and then this is going to break apart. So because I call it ammonium chloride, often helpful to think about what do I call it? Ammonium and chloride. So one of my ions is going to be the ammonium ion, and the other one is going to be the chloride. So here, this 4 isn't here to tell me that I need 4 ammoniums. That's actually part of what makes it ammonium, right? If there was more than one of them, there would be brackets around it, and there would be that little subscript. But I don't have that. So when I write this out, we're going to have the ammonium ion, so NH4 plus, it's going to be aqueous, and we are combining that, or plus, the chloride ion. Okay, so this is the one situation where you are allowed to have a subscript over on the product side when you write a dissociation equation. And that is when you have a polyatomic ion, because that subscript is part of the polyatomic ion, right? If I said NH plus, you wouldn't be like, oh, it's ammonium. So make sure that you leave those there. So that is how we write dissociation equations for ionics. This is why they're all electrolytes, because look, we've created species that are charged. They're moving around within the solution. So moleculars. We don't deal a lot with moleculars in chemistry, and that's because they don't really do anything. When we put a molecular into solution, literally the only thing that happens is we change the state. Nothing else changes. It doesn't dissociate, it doesn't ionize, it just dissolves. So if we take sucrose, which is sugar, right? We have C12H22O11. It's a solid. Okay, we put it into water, so it looks the same as what we did for dissociation equations. We put our arrow. Over top, we write out water. Okay, for the products though, literally all we're gonna do is we're going to change the state to be aqueous. That's all that's going to happen. So we're going to have C12H22O11, and it's going to be aqueous. And that's it. We're not really going to spend a lot of time with these because chemical reaction-wise, they don't really tend to do much. They're kind of unreactive because they are already bound together, and they're not looking to bind to something else. Okay, so all we're doing is changing the state when it comes to a molecular. There is an exception to this, though. There's one type of molecular that we get to do something special with, and that is an acid. So acids are molecular compounds, but what we find is they ionize in water, right? And usually you guys are familiar with by now the fact that acids have hydrogen, and they're going to produce that hydrogen ion in solution. But they don't do it the same way ionics do it. They don't do it because they're already made of ions and the ions break apart. They do it because they actually undergo a chemical reaction with water. And that chemical reaction ionizes the acid and forms ions. So because, again, we're forming ions in solution, they are going to be able to conduct electricity, and they're going to be considered an electrolyte. So when we are dealing with acids, we write ionization equations. Okay, so dissociation equation is for ionics, ionization equations is for acids. So this is actually going to look really similar to what we did for dissociation equations. The biggest difference is going to be that we actually include water in the equation because eventually we are going to be changing the water, and it does actually participate. So an example, we could take HCl. Generally, we talk about HCl as being a gas because originally HCl is a gas. But when we put it into water, someone just dropped something in the hall, totally scared me. This is going to ionize. I'm really jumpy if you haven't clued into that yet. Okay, so this is going to ionize, and what it's going to ionize into is hydrogen ions and chloride ions. So you might be thinking, well, that looks pretty similar to dissociation, and it kind of does. The only difference is this doesn't start as ions, it just produces them. Okay, we do also have to include that water.
All substitutes bring their keys to the main office. All substitutes, please bring your keys to the main office. Thank you.
Okay, so it looks pretty similar to a dissociation equation in that we are taking the acid, we are breaking it apart. Difference right now is we're including water. And you're going to see in a different lesson, we are going to look at the fact that if we have more than one hydrogen in the acid, we're going to do something a little bit different. Okay, but again, it's considered an electrolyte because we produced these ions in solution. And as soon as we produce ions in solution, we consider it to be electrolytic. So, dissolving. When we talk about dissolving, there is a process that happens. So, if I want to dissolve something, I have a solute and I have a solvent. There are bonds or attractive forces holding my solute together, right? If I have like salt crystals, something is holding them together, otherwise they would all fall apart. I have my water. Something is also holding that together, right? Because if you think about it, ever overfilled a water cup, it forms that bubble, right? There's an attraction between those water molecules. So the first thing that needs to happen for the two to mix together is we have to be able to break attractive forces in the solute. We have to be able to break attractive forces in the solvent. Once we break those attractive forces, we're able to form new attractive forces between the solute and solvent. Okay, you find that anytime you are breaking attractive forces, that requires energy and is considered to be endothermic. Anytime you are forming new attractive forces, that releases energy and is considered to be exothermic. So sometimes when we dissolve something, the amount of energy that we need to break is more than the amount of energy that we need when we release. And that's how you get like those instant cold packs. And sometimes it's the other way, where we only need to put in a little bit of energy to break it, and then we release a whole lot when we form it. And so overall, we get that release of energy, so it releases heat, and that would be what's happening in your hot packs. Okay, so energy to break attractive forces, energy released as you form new attractive forces. So when we talk about solutions, we classify them as being saturated or unsaturated. Okay, there's also supersaturated, but we don't talk about that in Chem 20 because it doesn't really do anything that we can calculate. It kind of defies the rules. So difference between a saturated and an unsaturated solution has to do with your solute. So if I only put a little bit of solute into water, most likely it's all going to dissolve. But if I put a whole lot of solute in, chances are only a little bit of it's going to dissolve, and some of it's going to stay at the bottom and is going to be unable to dissolve. So the difference between saturated and unsaturated is, were you able to dissolve at all, or were you not? So if a solution is considered to be unsaturated, that means you could have dissolved more solute in it. When you visually look at it, everything is going to be dissolved. You're not going to see any undissolved particles. Whereas when we talk about a saturated solution, that means you have put in more solute than is actually capable of dissolving. So you're going to visually see that there's undissolved solute sitting at the bottom of your container, right? And a lot of you have done this at some point in time. You've like made sugar crystals, either like on a stick or on a string, right? Normally you do that by putting a whole whack load of sugar into water and then putting your stick or your string into it. And then over time, you find that some of the stuff that was dissolved is going to crystallize out and form those nice crystals on the stick. And then some of the undissolved sugar at the bottom is going to dissolve to take its place. So we call that equilibrium. And we call it equilibrium because we have two processes happening at the same time that are the opposite of each other. And one of those is the crystals dissolving, and the other one is pieces crystallizing out. So because they're the opposite and they happen at the same time, we consider it to be equilibrium. So when we write dissociation equations, we need to pay attention to whether the solution is saturated or not. Because if it's an unsaturated solution, I'm going to use a single-headed arrow when I write that equation. But if it's a saturated solution and both processes are happening at the same time, we're going to use a double-headed arrow. So I know this is the arrow that's kind of in your notes, but usually we don't draw it that way. Let's see if it'll let me move my cursor around. Normally, I'll attempt to draw this by hand. We draw an arrow that looks like this. Okay, and that shows that this is turning into this, but that these are also at the exact same time turning back into that. Okay, so we have two processes that are the opposite happening at the same time. So if it says it's a saturated solution, you are going to use a double-headed arrow. If it said it was an unsaturated solution, then you get to use a single-headed arrow. Okay, in general, assume that it is unsaturated unless the question explicitly tells you otherwise. Then you can assume that it is saturated. Okay, so that concludes what we did in the first lesson. We basically kind of introed some of the solution stuff. So you should now be able to work through, I'd say, about half of the first assignment in the booklet. I think it takes you up to about question number 4. Okay, once you feel comfortable with that, you can go ahead and watch the next video.